I'm at the bottom. What about this plutonium stuff? What is the plutonium? I hear about plutonium in the movies. All right, so plutonium, what is this stuff? All right, well, plutonium is one of the byproducts of this nuclear reaction, right? So when you have the uranium 238, sometimes you end up having plutonium 239. Plutonium 239 obviously is pretty close to uranium. It is also fissionable, right? The plutonium 239 also likes to split up. When the 239 splits, then one of those neutrons gets absorbed into the 238. So if we have some plutonium 239, right, and then you got some uranium 238, which is left over. Remember, we're fissioning the 235 in the reaction. So this is the leftovers from your nuclear fuel, right? The original uranium 235. So the plutonium 239 that's there, if that loses a neutron, it can go into the 238, which then creates a uranium 239. And if we get that uranium 239 to undergo beta decay twice, then what happens is it becomes plutonium 239. Okay, so that's the difference between a uranium and a plutonium, is it gains two of those neutrons turn into protons. That's what happens in beta decay. And so basically what happens is we use that plutonium, which split up, we get energy from that, but then that then creates the uranium 239, which we can use to create more plutonium 239. This is called a short breeder reactor, sometimes a quick breeder reactor. And this can be used with the leftovers from your uranium 235 reaction. So you can actually get more energy out of it. Okay, now the problem is that because one plutonium 239 is going to create another one, and it creates several radioactive particles in the process, is that this is a very energetic process which keeps creating more and more fuel. It creates its own fuel. Now, yes, that can be good, but it also creates large amounts of waste, and it can also be used for nuclear bombs. And that really is the problem that comes up a lot of times as well. Do we want countries to have nuclear fuel to be able to turn uranium 235 into uranium 238 if that means they're also going to be able to create uranium 239, which can be used to create nuclear bombs? So that's kind of one of the issues that comes up with plutonium, and that's part of it. We're not going to go into that too much because that's not the main way that's used to make energy. At this point, the other thing that we should talk about is safety issues. Well, obviously, yes, there are safety issues associated with radioactivity. You've got alpha decay, you've got beta decay, you've got gamma decay, and then you've got a bunch of extra neutrons flying around. Okay, so really, what's important here, right? Well, the alpha decay and the beta decay and the neutrons, right? Most of these, didn't want that to happen, but the alpha decay, the beta decay, and the neutrons, those are all rather large particles. Okay, even the beta decay, which is electrons, those can be stopped by steel, right? That's the purpose of the steel reactor container where your nuclear power is taking place, right? When we had that pitcher and the heat exchanger, there is a steel encasing. That stops all of the alpha decay, the beta decay. That steel is thick enough that those particles can't get out. Now, the gamma decay is highly energetic, but it's also just high energy light, right? So is it dangerous? Yes. It's less likely to cause a problem, but if it does cause a problem, then it creates big problems. So that's why we then put the cement around the outside, and you put thick enough cement on the outside, and the gamma is not getting out either. All right? So that's why you have the reinforced concrete on the outside. That again will stop the neutrons, but it will also stop any neutrons that get out. But it'll definitely stop the gamma rays as well. There's all sorts of emergency safety mechanisms, which that was the problem in Fukushima. In Fukushima, the earthquake and the tidal wave shut down the generator that actually ran those safety mechanisms. And so that's why there was a meltdown there and all sorts of problems. Generally, there are robots and computers and other things that control these control rods, so even stupid humans can't mess it up. But there's always somebody watching it and making sure that even the computers are doing the right thing and making the right job. All right. So that's basically the idea of nuclear power, and really the safety issues are, for the most part, non-issues. Now, obviously, they're not non-existent because there have been 3 problems in the last 80 years, but they do happen. But for the most part, they are very easily taken care of, and there are not safety issues as long as radioactivity is treated with the proper respect and we are safe about it as we go. Okay? So here's a question for you. What would a Sankey diagram for nuclear power look like? Well, there you go. You've got the energy coming in from the uranium. Okay? You are going to get some heat losses, right? You're going to lose some energy there. Some of the fuel, there's still going to be some uranium-235 in there. You're not going to get it all out, right? And there's going to be some energy left in some of those particles, right? That's part of the problem with the nuclear fuel, is that it is radioactive for years afterwards, and so there is some energy left there. That's a problem. You also require energy to do this, right? You have to be shooting those neutrons in to be able to get the process started. Well, neutrons you can't just stick a neutron inside of a gun and go, pew, I'm done, right? It takes energy to be able to create a situation where you can get those neutrons coming out so that you can get the process to occur. In the end, here's your electricity. This much. Out of that, what percentage would you say that is? What would you say the efficiency is? Most people say about 10 to 15%. Right? Looking at how wide this is compared to how wide that is, right? 10 to 15%, maybe 20 if you're lucky. But wait. I thought coal was 35% and natural gas was like 50%. So why does Mr. Bywater keep saying that nuclear power is the way of the future and it's so great, other than the fact that it kills less people? Well, you have to remember this. Right? You have to remember that uranium has an energy density of 1.5 times 10 to the 15th, right? It has 10 billion times more energy, right? You take a block of uranium, and we're just talking about a block, like a handful of uranium, and that handful will have 10 billion times more energy than the same size of coal. So you think about the energy required, the amount of oil required to run the trucks and the machines and everything else to get the coal from where you mine it out to the power station, and you consider how much energy it would take to get that amount of uranium and then move it to the power station. It takes significantly less energy and work to be able to get the fuel, and then you get a lot more out of that fuel. Significantly more. It doesn't matter that it's half as efficient because you're getting 10 billion times more energy, right? So this is why these ideas of specific energy and energy density are important, because it gives us a much better idea of how much energy we're actually going to get compared to those efficiencies. Efficiency isn't everything. Is it important? Yes, but it's not necessarily everything that we need. All right. I would like to close by just looking at one question here. All right. When one uranium-235 nucleus undergoes fission, 3.2 times 10 to the negative 11 joules of energy is released. The density of uranium-235 is 1.9 times 10 to the 4th kilograms per meter cubed. Calculate for uranium-235 the specific energy. Okay, now specific energy, remember, is joules per kilogram. Specific means per kilogram, and energy, of course, is joules. So can we calculate? Can we get joules per kilogram? All right, well, this says one uranium nucleus, so one uranium-235 okay, allows us to get 3.2 times 10 to the negative 11th joules of energy. So I'm going to create, you guys have seen me use this before, but this is my conversion tool. I've got 1 uranium-235, which is 3.2 times 10 to the negative 11th joules. Okay, now the joules are where I want. I do want joules on the top, but I need kilograms on the bottom. So how can I get 1 uranium-235 particle and turn that into kilograms? Well, here's the process. I know that there are 6.02 times 10 to the 23rd particles in 1 mole. So I'm going to turn the particles into moles. And in order to do that, I need the 6.02 times 10 to the 23rd right there. Okay, so that then is going to turn it, the particles are going to cancel out, and I'm going to be left with moles. Now, I also know that uranium-235 means that there are 235 grams in 1 mole. So I can use that here. I want the moles to cancel out. So I'm going to put that there, and then I'm going to put the 235 grams on the bottom. Okay, so I'm just using those conversions that I already know. Now it'll be in grams. Now I need it in kilograms. So I know there are 1,000 grams in 1 kilogram. Again, I want the grams to turn into kilograms, and I want the grams to cancel out. And then I put in the 1,000 grams in 1 kilogram, and I got it. So now I just need to multiply the things on the top, divide by the things on the bottom, and that should get me to the final answer. So why don't you try it out and see if you get the same thing that I do. All right, so I end up getting 8.19 times 10 to the 13th, and this is, I still got the joules on top, and I got the kilograms on bottom, and everything else canceled out. So 8.19 times 10 to the 13th joules per kilogram is the specific energy of my uranium-235. All right, now the energy density, well, energy density, remember, is just joules per volume. Density is per volume. And so, in order to get energy density, I just need to take this, I need to turn the kilograms into meters cubed. So following the same process as before, I want the kilograms, which are now on the bottom, to turn into meters cubed, and I want the kilograms to cancel out. And right here, I've got that it's 1.9 times 10 to the 4th kilograms in 1 meter cubed. And so I just take my answer and I multiply it by 1.9 times 10 to the 4th. And hopefully you get the same thing that I do, about 1.6 times 10, I guess I had 3 sig figs there, so 1.56 times 10 to the 18th power, and the units are joules per meter cubed. Ta-da! That's it for nuclear power, at least for now.